the second one. So now we start the second part, which is about exotic two spheres. And we will talk about knots and the unknotted conjecture in four-dimensional manifold. And we will talk about two operations on manifolds that help you construct new ones. We will talk about the exotic four manifolds that we have seen earlier in the part one, the infinitely many smooth structures on K3. And we will talk also about their stabilization, like the fourth theorem. And finally, we will derive from that, all this that we have seen, we will use to get some exotic two spheres. So first of all, we can talk about classical knots, which is a smoothly embedded S1 in S3. And we call two knots K1 and K2. We call them equivalent if there exists an orientation preserved in homeomorphism or diffeomorphism from the pair S3K1 to the pair S3K2. By this, I mean it sends K1 to K2. It's a map from S3 to S3 and it sends K1. So this is, for example, a table of knots that you can find on Wikipedia if you Google. It has the unknot, which is the trivially embedded S1. The second one is the trefoil. The third is the figure 8 knot. And they are named based on how many intersection points the diagram has. So this one has 3, you can see. This one has 4. And so on, 5 and 6 and 7. So these are all the prime knots up to 7. Suppose, yeah. So now we can try to work with knots in dimension 4, for example. Like we can try to take embeddings of S1 in S4, but that turns out to be trivial because all these embeddings are going to be smoothly isotopic. So we need to raise the dimension of the knot to get anything meaningful. Because anything of dimension 1 in dimension 4 is going to be smoothly isotopic. Anywhere you embed it will be the same. So we can define the following. A 2 knot is an embedded S2 in S4. So instead of taking S1, we take S2 in S4. And for one of the ways to distinguish 2 knots is, for example, you can take, one of the ways to distinguish them is to consider the fundamental group of the knot complement, so S4 minus the embedded S2. And this will be a 2 knot invariant. So if 2 knots are the same equivalent, they will have the same fundamental group of the complement. And then like it's an invariant, but it's not the full one, because there are knots that have the same fundamental group of the complement, but they are different knots. So you want to ask whether this property, this failure does also fail for the trivial knot, like the unknotted S2 in S4. And an important conjecture says that it is we call this an unknot detector. So is there a unique up to equivalence 2 knot K in S4 with the fundamental group of S4 minus K to be Z? This is the fundamental group of the trivial knot, the complement of it. So are there other knots, 2 knots that will have the same fundamental group of the complement? Well, the topological case is pretty much settled by Friedman, which says that the unknotting conjecture is true in this case. So this knot is unique up to topological equivalence. So you can, if you remember the definition of equivalent, here you will have a homeomorphism. You will not have diffeomorphism, you will have a homeomorphism. This is the conclusion of Friedman, also in the same 1982 work. So one can also consider closed surfaces other than S2 to define a two knot. Like you can take a broader definition and consider all surfaces of genus higher, also high genus, and see if they will, if this unknotted conjecture will still hold. So the theorem by Conway and Powell says that the unknotted conjecture is true also in the topological category for surfaces of genus higher than 2, so from 3 and above. In the case of 2 and 1, it is still open, I think. The smooth unknotted conjecture, which is that whether this equivalence will be smooth instead of topological, so diffeomorphism instead of homeomorphism, this is still open and we don't know much. But there has been counterexamples for variation of it. Usually, all these variations are not in S4, like you change the ambient for manifold, and you can find counterexamples. So, for example, the unknotted conjecture, the smooth one, needs to be smooth in S4, and the two knot has genus 0, so it's a sphere. And since it's in S4, the homology class of the knot is 0, because S4 doesn't have second homology. And the fundamental group of the complement is gonna be the integer Z. So Friedman proved it in the topological one, so without the smoothness conclusion. So, and Conway and Powell proved it for genus higher than 2. And then in 1997, the first smooth counterexamples, I think, were by Fintucci and Stern in 1997. So they don't take S4, they take higher, bigger manifolds, and they construct surfaces of higher genus, and they are not null homologous and not the same fundamental. But these surfaces, they constructed surfaces that are exotic. So these surfaces are gonna be topologically equivalent, but smoothly not equivalent. So they will satisfy this. There will be a homeomorphism that sends one to the other, but there will not be a diffeomorphism that sends one to the other. And such surfaces are called exotic surfaces. And then in 2008, Kim and Ruberman proved it with the extra condition that pi1 is Z, so to approach the smooth unknotted conjecture. In 2019, Hoffman and Sunukian proved it also for null homologous surfaces. They proved it for tori, I think, so the genus was still higher than 0. They constructed these exotic tori. And in 2020 and in 2022, there's joint work in me and Malik and Torres. We added we constructed smooth spheres, so genus is 0, and null homologous with pi1 equals Z that are exotic. So it added the extra condition that the genus is 0, that they are spheres. So first we will start to discuss the idea of the proof and see how we can get to it more or less naturally. But first we will need to discuss two operations. The first one is called surgery on a four manifold. So if you have an orientable closed or oriented closed four manifold M and a loop gamma in M, we can remove tubular neighborhood of gamma. So you have the bound, you will get a boundary if you remove that, if you remove tubular neighborhood of gamma. But this boundary is the same as that of the tubular neighborhood, which is diffeomorphic to S1 times D3. And the bound, so you know that the boundary is an S1 times S2. But you also know that this is also the boundary of a D2 times S2. So you can glue back D2 times S2 instead of S1 times D3. So you have removed an S1 times D3 and you glue back at D2 times S2. And the resulting manifold is the result of surgery on M along gamma. So This is what surgery is along the loop. Now, when you added this D2 times S2, you should remember the S2, this sphere. There's a special sphere that is important to remember. It's called the belt sphere, which is, you can see it as a point times S2 in D2 times S2. So why is this sphere important? Because this sphere lets you reverse the surgery. We call this surgery along spheres. If you remove this sphere and glue back an S1 times D3, you will get your previous manifold back just by definition of the previous surgery. So yeah, so this surgery operation is reversible. You don't lose much. You don't lose a lot of information because you can go back always to your previous manifold. There's this belt sphere that holds that memory. So example, so if you take M to be S1 times S3, if you surgery along S1 times a point in this manifold, you will get an S4. And this, the belt sphere is gonna be the unknotted S2, or the one given by the equator. So in S4. So if you reverse that surgery, you will get back S1 times S3. Okay, so that's for surgery. Now for fiber, not the second operation is called the fiber sum. And it's that if you have two tori, T1 in M1 and T2 in M2, where M1 and M2 are closed orientable for manifolds oriented, with trivial, these torides should have trivial normal bundle. So what you can do is you can remove these torides and glue back the boundaries of M1 times M2. So you have T1 and T2 in M1 times S2. You remove them, you get the same boundary both in M1 and in the complement of T1 in M1 and that of M2. And you can glue these boundaries together. This way you get a manifold called the fiber sum between M1 and M2. And you denote it this way with a ds and an f, small f. So this is like a more general connected sum. So the connected sum, you had a point, you remove the point, and in this case you have a torus, you remove a torus. So now we go to the Fintuchel-Stern construction of exotic four manifolds. So first, there is some important invariant of classical knots, so S1 in S3. This invariant is called the Alexander polynomial. It's a Laurent polynomial with integers coefficients. So this polynomial comes from some infinite cyclic cover of the complement of the knot, but that doesn't interest us. We will see what interests us is that there are infinitely many knots with pairwise different Alexander polynomials. So you have infinitely many possible Alexander polynomials. This will be important later. So for example, okay, the unknot has a polynomial with 1. The 3-fold, this knot is called the 3-fold. I made a mistake. I think one of them should be a reverse crossing, but okay, this will be T inverse minus 1 plus T. And this one will be the figure 8 knot. We'll have this polynomial minus T inverse plus 3 minus T. So another invariant, but not of knots, this time of smooth form manifolds, is called the Seiberg-Witten invariant, which is an element of the group ring of the second homology form. This is just, think of it as formal combinations of the elements of the second homology somehow to make them into a polynomial somehow. But anyways, this invariant comes from physics or from gauge theory, and it was introduced by Seiberg and Witten. And Witten is a physicist, theoretical physicist. So this is one of the times where physics helped math, I guess. So now what Fintuchel and Stern do is that if you take closed orientable simply connected form manifolds X with non-zero Seiberg-Witten invariant, and you suppose there is a smoothly embedded torus T with a trivial normal bundle, and the fundamental group of the complement is also trivial, you fiber sum X and T with S1 times S3, but with the tori coming from S1 times the knot in S3. So this manifold, we call it XK. So you take X and you fiber sum it with S1 times S3, but the tori you are choosing is S1 times a knot. So you can check by Friedman's classification theorem of earlier that this manifold is homeomorphic to X. It will have the same intersection form. However, the theorem Fintuchel-Stern, what they proved is that the Seiberg-Witten invariant of XK is going to be the Seiberg-Witten invariant of X multiplied by the Alexander polynomial evaluated sum. So XK is not going to be diffeomorphic to X. They have different Seiberg-Witten invariants. And this will be the case for infinitely many knots because there are, we've already said that there are infinitely many Alexander polynomials. So this was how Fintuchel and Stern constructed their exotic form manifolds. And so you see that they are homeomorphic by Friedman theorem, and then you see that they are not diffeomorphic by Seiberg-Witten theory. And you get exotic form manifolds. For example, you might say that this X is which manifold will satisfy the conditions on X. The K3 surface will satisfy them. So the K3 surface has infinitely many smooth structures. Now stabilization. So in part one, we mentioned Wahl's theorem that if two smooth, closed, simply connected form manifolds M1 and M2 are homeomorphic, then there is an integer such that if you connect sums with R copies of S2 times S2, you will stabilize this exoticness and you will make them diffeomorphic. So in this case, in the particular case of Fintuchel and Stern construction, Akbulut in 2002 proved that XK connected sum S2 times S2 is diffeomorphic to X connected sum S2 times S2. So R equal 1 is enough in this case, which is due to Akbulut. So now we know what we need to start trying to find exotic two spheres. So if you take X to be smooth, closed, oriented, simply connected form manifolds with some conditions here, non-zero Seiberg-Witten and a condition on the second homology. And if you suppose that there are two disjoint torized T1 and T2 with simply connected complement as before, then what you want to do is you want to use the first tori to do the fiber sum of Fintuchel and Stern. So with S1 times S3 along S1 times M0, and the other tori to do the fiber sum with another manifold, a certain closed manifold we will call N. So the first one is the Fintuchel-Stern construction. It will give us an exotic structure. The second one will give us a manifold, will raise the fundamental group to Z. So we will call the result XKZ. So this is a diagram of the idea, maybe, is that if you take X and it has two tori here, you can see, and you use the first tori, the first torus, to make the exotic structure by connect summing with S1 times S3, by fiber summing with S1 times S3, and you use the second torus to fiber sum with a certain manifold N, so that you will get a manifold with fundamental group C. So this is XKZ here. Let's say that gamma is the generator of the fundamental group. So Y1 is generated by gamma. this is the loop. We will come to the second part later. So by theorem of Hamilton and Teichner, we know what XKZ is, even if it has non-trivial fundamental group. Remember that Friedman's theorem works for simply connected manifolds. But in the case of not simply connected manifolds, it doesn't work. Instead, Friedman himself proved some variation of it to fundamental group Z, which is our case, and then Hamilton and Teichner improved on that, made it even nicer. So in this case, we know that just by the intersection form that XKZ is homeomorphic to X connected sum S2 times S2 connected sum S1 times S3. So we know its topology is, we know what XKZ is topologically, but we don't know what it is smoothly. We know that it's going to be this, but not diffeomorphic to it for infinitely many cases. However, we can do a surgery to kill the S1 times S3 factor. So if we go back here, you will have this gamma, the generator of the fundamental group. If you do surgery along this loop, you will get new manifold X, and this new manifold will be X connected on S2 times S2. Why? It will actually, if we surgery this along a generator of the fundamental group, so along gamma, you get a manifold diffeomorphic to XK connected some S2 times S2. One can show this. And by Akbulov's result, so we can, this is an exotic manifold stabilized. So we know that this is diffeomorphic to X connected sum S2 times S2. So actually by killing something here in the pi one, bit away from here. So if you kill this gamma, you will actually kill the exoticness of the manifold. But what remains to you is the belt sphere. We said that the belt sphere remembers the previous manifold. So call this belt sphere Sk. If you surgery along it, you will get back your manifold. So as we said, the last surgery leaves a belt sphere Sk for each knot K. And one can ask the question, are these spheres smoothly isotopic? So if they were smoothly isotopic, then surgery along each one of them will give the same manifold. However, we know that surgery along SK1 and SK2 will give XK1Z and XK2Z. This, you are going back to the previous manifold, which were exotic for many knots by Fintuchel's term. So our theorem is that there is an infinite, all these spheres are gonna be topologically equivalent, but pairwise not smoothly equivalent. And nullhomotopic two spheres in X connected sum S2 times S2. And their fundamental, moreover, the fundamental group of their complement is Z. Yeah, we can have also the same statement if you remove the D4 from the X connected sum S2 times S2, you will remove also a disk from the spheres, these exotic spheres, and the disk that remains also gonna be exotic. So in general, these spheres are belt spheres of surgery on exotic stuff. So they have the memory of that exoticness, and this will make them exotic spheres themselves. So they are topologically equivalent, but not smoothly equivalent. And these are these spheres here in this manifold. And that's it. Thank you for your attention. Is there any questions?